Hi, welcome to another Cold Fusion video. In the last video, complete with its own quantum upload, we talked a bit about how quantum computers work and their implications for the world, but some of you either didn't quite grasp it or wanted a deeper, more literal explanation. And I agree, so I thought I'd make this video to bring you up to speed.
You are watching Cold Fusion TV.
The following information is from my book, New Thinking. I talked to some people in my university and had someone who actually worked with quantum computers read over it to make sure that it was all technically correct. So from the last video, we know that quantum computers can solve problems that would take infinitely long on a classical computer. Things such as modelling the brain and modelling weather systems, etc. But let's take a deeper look at how they work. We covered that regular computers process data as binary bits, represented either as a 1 or a 0. A quantum computer's equivalent data is known as quantum bits or qubits, which can exist in both 0 and 1 states at once, allowing multiple computations to happen simultaneously. These states in a particle are called spin, but there's really no need to know what that is for the purpose of this video. This simultaneous state of both 0 and 1 is like a kind of soup of probabilities called a superposition. This makes it possible to store and manipulate vast amounts of information with a relatively small amount of particles. So what is a qubit made from? While a normal computer's bits are made from tiny transistors, a qubit can be anything that exhibits quantum behavior: an electron, an atom, or even a molecule. That is, if the environment is right. More on this later. So I just want to solidify why the superposition aspect is so important. As I said in the last video, our world and reality itself is quantum in nature. Real-world quantum systems can't be modelled on a classical computer without making poor approximations. For the two simple molecules in this example here, a classical computer is off by a factor of 70 to 200%. Think about it. Modelling such a simple compound as calcium monofluoride makes our best supercomputers completely useless. Our current machines are so inaccurate because the electrons in the real world that are orbiting around these atoms are themselves in superposition. These electrons exist in multiple states at once, and we can't model that properly with classical computers. Calculating all the possibilities is just too much for them. Quantum computers, on the other hand, can leverage the fact that they themselves also operate using superposition. This kind of modelling, which is impossible today, will become routine because of the sheer amount of data that quantum computers can hold. Richard Feynman, who was instrumental in the very formation of quantum physics, first proposed this concept. To get that exponential processing speed up, the qubits must be able to communicate. The fate of all qubits are linked together in a process called quantum entanglement. Entanglement is just a relationship between two superposition particles. The state of one determines the state of the other. So basically, all this means that in quantum computers, entanglement along with superposition helps the system store all possible solutions at once. So what are quantum computers good at? As it turns out, as far as we know, quantum computers are good at things that have a small input and output while having a vast array of possibilities. Let's take a look at a few examples to solidify this idea. So for modelling complex molecules, the input is the number of particles in their starting state, while the output is what happens after a given time. The possibilities of what happens in between that time are almost infinite. Another example, breaking encryption. In 1994, American mathematician Peter Shor of Bell Labs found a theoretical way to use quantum computers to break codes that relied on the factorization of large numbers into primes. This doesn't sound like much at first, but many online security systems, from banking to encryption, rely on the principle that it's currently almost impossible to take a very large number and figure out what the prime factors are. The best algorithm known for classical computers uses a number of steps that keeps increasing exponentially until it takes billions of years. Using the algorithm by Peter Shor, called Shor's algorithm, a quantum computer could perform the task in just a number of hours. In this case, the input is a single large number, and the output is how many sets of prime numbers multiply together to give that large number. Again, the possibilities here are almost infinite. One last, but simpler example. Finding the longest distance between two cities in Japan. The input is the map data, road distances, etc. It's large, but nothing that a classical computer couldn't handle. The output is just one number, the longest distance. And the possibilities? Well, it seems like a simple problem, but if you think about it, there's an almost infinite number of routes you could take. In fact, this very class of problem is forever unsolvable using classical computers. This class of problem is mathematically called an NP-complete problem. There are many other real-world problems of this type, from weather patterns and climate change to boosting artificial intelligence training, from looking at patterns in stock market data or in recordings of brain activity, not to mention gene analysis and drug delivery, as well as many other things. Unlike with today's computers, finding these patterns could become routine, requiring no detailed understanding of the subject problem, and this is what makes quantum computers so interesting. So this all sounds good, but there are still some hurdles. The first problem is due to quantum physics itself. An observer can never directly know all the vast number of qubit states at the same time. All an observer knows is the probability of what state the qubits will be in. The very act of observing or measuring the overall state of the quantum computer's qubits will force the system to decide on which state they're in. So instead of the quadrillions of answers, we can only see one, and that's another quirk of the quantum world. So how do we make this useful? Well, the answers that come out of quantum computers are in the form of a probability. If you repeat the question, the answer will change slightly and the quantum computer state will begin to approach the theoretical percentage or correct answer the more times you repeat. You might ask the quantum computer several times, but getting a good answer on the second or third attempt may still be much faster than waiting for a certain answer on a classical computer. So this next part is pretty crazy. In order for a quantum system to push towards the right answer when asked repeatedly, the code must be designed so that the qubits are likely to be in the correct state for a given problem, hence give us the right answer. Fascinatingly, the quantum code is designed to use the wave-like properties found in particle physics to cancel out the wrong answers and amplify the correct answer. The answer can then be detected and viewed. The manipulation of nature through code is called a quantum algorithm. Mathematicians and scientists around the world are on a race to build these algorithms for when capable quantum computers arrive. So with all of this said, why don't we have powerful quantum computers now? It's mostly because of the second problem with building them, the practicality of maintaining a quantum environment. In my book, I refer to qubits as very shy divas. To be in their quantum superposition state, that is, being in multiple states at once, they need to be comfortable. Qubits must be free from all radiation and kept at a temperature just above that of absolute zero. If the particle interacts with anything, the quantum effects are scared away. Any slight disturbances such as light particles, radiation, or even quantum vibrations can snap the particles out of their superposition state. This voids the entire advantage of the machine. Right now, we can only achieve a quantum superposition for a tiny fraction of a second, not long enough to carry out a useful algorithm. Mastering this fragile quantum state still remains one of the biggest challenges for engineers and scientists to build a practical quantum computer. So that brings us to the next and final point. How do you actually build these things? Our current quantum computer designs consist of two main types for construction, the superconductor type and the spin type, that is, the use of small particles. The most popular spin method uses single electrons within silicon to create qubits. The reason for this is that the infrastructure for nanoscale silicon components is already established, so it makes economic sense to just leverage what we already have for a new kind of computing. These electrons within the silicon are called quantum dots. Only several nanometers in size, they can operate at slightly higher temperatures, making them more stable. Research on this method only started to pick up in 2017. The older, more established qubit uses a metallic superconductor to create a quantum state. Superconductor qubits defy the misconception that the strange quantum effects are impossible for larger objects. This is not strictly true. The way we get large objects to produce quantum states is by letting the material reach that fragile diva state. This is done by subjecting them to a super cold vacuum environment. The result is a qubit that's visible to the naked eye. The most popular method is a super cold metallic ring, almost at absolute zero. At these temperatures, electrons can flow around forever without ever bumping into anything. Stranger still, all these electrons flow clockwise, but at the same time, all the electrons also flow counterclockwise. If the clockwise flow is read as a 1 and the counterclockwise flow is read as a 0, it's essentially a superposition qubit. The superconductor method is how D-Wave, IBM, and Google quantum computers work. So to round out, let's take a look at a few achievements. So right now, the best quantum computer we have is using the quantum dot method, though most of those qubits are used for error detection. On the road to building a quantum computer, MIT scientists have reported the discovery of a new triple photon form of light. An Australian team has set the record for the most accurate 1-qubit gate in a silicon quantum dot. They had a remarkable accuracy of 99.96%. And also, many other companies are joining in the quantum race, from startups all the way to established names like Honeywell. IBM also wants a commercial quantum computer in as little as 3 years. So where does this all leave us? So as concluded in the last video, quantum computers hold great promise, but it's still going to be multiple decades before we have a meaningful machine. And I'd say that when the first breakthroughs start to happen, we'll enter a hype cycle where the media and everyone picks it up thinking that quantum computers are around the corner, but they're just not ready yet, and expectations will probably follow before the real breakthroughs actually start to happen in a couple of decades. Hopefully this video answered a lot of your questions from the last video. If you do want to know more about this, and other technology all the way from the Industrial Revolution to quantum computers and AI, be sure to check out my book. The audiobook version is also available in the description below. So that wraps up the video, thanks for watching. It might take a few listens to process all of this information, but once you do, it becomes clear just how amazing this topic of quantum computers is. It's one of the most fascinating topics I've ever come across. Anyway, this has been Dagogo, and you've been watching Cold Fusion, and I'll catch you again soon for the next video. Cheers guys, have a good one.
Cold Fusion. It's new thinking.